1.2.2 Atoms and Molecules. An atom is the smallest particle of an element that has the properties of that element and can enter into a chemical combination. Consider the element gold. For example, imagine cutting a gold nugget in half, then cutting one of the halves in half, and repeating this process until a piece of gold remained that was so small that it could not be cut in half, regardless of how tiny your knife may be. This minimally sized piece of gold is an atom, from the Greek atomos, meaning indivisible, figure 1.12. This atom would no longer be gold if it were divided any further. Figure 1.12. A. This photograph shows a gold nugget. B. A scanning tunneling microscope, STM, can generate views of the surfaces of solids, such as this image of a gold crystal. Each sphere represents one gold atom. Credit A. Modification of work by United States Geological Survey. Credit B. Modification of work by Erwin Rossen/Wikimedia Commons. The first suggestion that matter is composed of atoms is attributed to the Greek philosophers Leucippus and Democritus, who developed their ideas in the 5th century BCE. However, it was not until the early 19th century that John Dalton, 1766 to 1844, a British schoolteacher with a keen interest in science, supported this hypothesis with quantitative measurements. Since that time, repeated experiments have confirmed many aspects of this hypothesis, and it has become one of the central theories of chemistry. Other aspects of Dalton's atomic theory are still used but with minor revisions. Details of Dalton's theory are provided in the chapter on atoms and molecules. An atom is so small that its size is difficult to imagine. One of the smallest things we can see with our unaided eye is a single thread of a spider web. These strands are about 1/10,000 of a centimeter, 0.0001 centimeter, in diameter. Although the cross-section of one strand is almost impossible to see without a microscope, it is huge on an atomic scale. A single carbon atom in the web has a diameter of about 0.00000015 centimeter, and it would take about 7,000 carbon atoms to span the diameter of the strand. To put this in perspective, if a carbon atom were the size of a dime, the cross-section of one strand would be larger than a football field, which would require about 150 million carbon atom dimes to cover it. Figure 1.13 shows increasingly close microscopic and atomic level views of ordinary cotton. Figure 1.13. These images provide an increasingly closer view. A cotton boll. B. A single cotton fiber viewed under an optical microscope, magnified 40 times. C. An image of a cotton fiber obtained with an electron microscope, much higher magnification than with the optical microscope, and D and E. Atomic level models of the fiber. Spheres of different colors represent atoms of different elements. Credit C. Modification of work by Featheretart Wikimedia Commons. An atom is so light that its mass is also difficult to imagine. A billion lead atoms, 1 billion atoms, weigh about 3 multiplied by 10 to the power of -13 grams, a mass that is far too light to be weighed on even the world's most sensitive balances. It would require over 300 trillion lead atoms, 300 trillion, or 3, multiplied by 10 to the power of 14, to be weighed, and they would weigh only 0.00000001 gram. It is rare to find collections of individual atoms. Only a few elements, such as the gases helium, neon, and argon, consist of a collection of individual atoms that move about independently of one another. Other elements, such as the gases hydrogen, nitrogen, oxygen, and chlorine, are composed of units that consist of pairs of atoms, figure 1.14. One form of the element phosphorus consists of units composed of 4 phosphorus atoms. The element sulfur exists in various forms, one of which consists of units composed of 8 sulfur atoms. These units are called molecules. A molecule consists of 2 or more atoms joined by strong forces called chemical bonds. The atoms in a molecule move around as a unit, much like the cans of soda in a 6-pack or a bunch of keys joined together on a single key ring. A molecule may consist of 2 or more identical atoms, as in the molecules found in the elements hydrogen, oxygen, and sulfur, or it may consist of two or more different atoms, as in the molecules found in water. Each water molecule is a unit that contains two hydrogen atoms and one oxygen atom. Each glucose molecule is a unit that contains 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. Like atoms, molecules are incredibly small and light. If an ordinary glass of water were enlarged to the size of the Earth, the water molecules inside it would be about the size of golf balls. Figure 1.14. Hydrogen, H2. Oxygen, O2. Phosphorus, P4. Sulfur, S8. Oxygen atom. Hydrogen atom. Water, H2O. Carbon atom. Carbon dioxide, CO2. Glucose, C6H12O6. Figure 1.14. The elements hydrogen, oxygen, phosphorus, and sulfur form molecules consisting of two or more atoms of the same element. The compounds water, carbon dioxide, and glucose consist of combinations of atoms of different elements. Chemistry in everyday life. Decomposition of water, / production of hydrogen. Water consists of the elements hydrogen and oxygen combined in a 2-to-1 ratio. Water can be broken down into hydrogen and oxygen gases by the addition of energy. One way to do this is with a battery or power supply, as shown in Figure 1.15. Figure 1.15. Water. 2H2O, L. Hydrogen. 2H2, G. Oxygen. O2, G. Figure 1.15. The decomposition of water is shown at the macroscopic, microscopic, and symbolic levels. The battery provides an electric current, microscopic, that decomposes water. At the macroscopic level, the liquid separates into the gases hydrogen, on the left, and oxygen, on the right. Symbolically, this change is presented by showing how liquid H2O separates into H2 and O2 gases. The breakdown of water involves a rearrangement of the atoms in water molecules into different molecules, each composed of 2 hydrogen atoms and 2 oxygen atoms, respectively. 2 water molecules form 1 oxygen molecule and 2 hydrogen molecules. The representation for what occurs, 2H2O, L, yields 2H2, G, plus O2, G, will be explored in more depth in later chapters. The two gases produced have distinctly different properties. Oxygen is not flammable but is required for combustion of a fuel, and hydrogen is highly flammable and a potent energy source. How might this knowledge be applied in our world? One application involves research into more fuel-efficient transportation. Fuel cell vehicles, FCV, run on hydrogen instead of gasoline, Figure 1.16. They are more efficient than vehicles with internal combustion engines, are non-polluting, and reduce greenhouse gas emissions, making us less dependent on fossil fuels. FCVs are not yet economically viable, however, and current hydrogen production depends on natural gas. If we can develop a process to economically decompose water, or produce hydrogen in another environmentally sound way, FCVs may be the way of the future. Figure 1.16. Hydrogen. Unused hydrogen. Anode. Proton exchange membrane. Cathode. Electric power. Oxygen. Water. Figure 1.16. A fuel cell generates electrical energy from hydrogen and oxygen via an electrochemical process and produces only water as the waste product. Chemistry of cell phones. Imagine how different your life would be without cell phones, Figure 1.17, and other smart devices. Cell phones are made from numerous chemical substances, which are extracted, refined, purified, and assembled using an extensive and in-depth understanding of chemical principles. About 30% of the elements that are found in nature are found within a typical smartphone. The case/body/frame consists of a combination of sturdy, durable polymers composed primarily of carbon, hydrogen, oxygen, and nitrogen, acrylonitrile butadiene styrene, ABS, and polycarbonate thermoplastics, and light, strong, structural metals, such as aluminum, magnesium, and iron. The display screen is made from a specially toughened glass, silica glass strengthened by the addition of aluminum, sodium, and potassium, and coated with a material to make it conductive, such as indium tin oxide. The circuit board uses a semiconductor material, usually silicon, commonly used metals like copper, tin, silver, and gold, and more unfamiliar elements such as yttrium, praseodymium, and gadolinium. The battery relies upon lithium ions and a variety of other materials, including iron, cobalt, copper, polyethylene oxide, and polyacrylonitrile. Figure 1.17. Case components. Polymers such as ABS and SLASH are metals such as aluminum, iron, magnesium. Processor components. Silicon, common metals, copper, tin, gold. Uncommon elements, yttrium, gadolinium. Screen components. Silicon oxide, glass, strengthened by addition of aluminum, sodium, potassium. Battery components. Lithium combined with other metals such as cobalt, iron, copper. Figure 1.17. Almost 1/3 of naturally occurring elements are used to make a cell phone. Credit. Modification of work by John Taylor.